Hello everyone from Math 1340, Statistics. It's Professor Wenson here again with a video on your KnewtonAlta homework for section 4.3, titled the Binomial Distribution. Now, we've seen in the previous couple sections these things called probability density functions or probability distribution functions, PDFs, for a discrete random variable. The binomial distribution is just a very special example of one of these discrete probability distribution functions, as we'll see. Alright, so here I am. Again, you're not going to see the word preview. In section 4.3 binomial distributions homework, you got your mastery bar and all that, the objectives. You can see there are 3 objectives for this particular section. And this one that I'm currently on for this question is understand the parameters of the binomial distribution. Now hopefully that word looks familiar, parameter. Remember there were parameters and there were statistics. And a parameter was any number that described an aspect of a population. And when we talk about probability distribution functions or probability density functions, right, we're talking about all possible outcomes. Right? You're listing all possible values of the random variable. So that's why we're talking parameter, because the word all is in there. You have all possible outcomes. Alright, so I'm going to go on more instruction. It's the first time I'm seeing this objective. Alright, so first of all, we need to know what the binomial distribution is. Right? What do they mean by binomial distribution? Then we'll get into the parameters, and that's what they start off with here. So a probability distribution function, or a probability density function, as you've seen, is a pattern. You try to fit a probability problem into a pattern or a distribution in order to perform the necessary calculations. These distributions are tools to make solving probability problems easier. Each distribution has its own special characteristics. Learning the characteristics enables you to distinguish among the different distributions. Some of the more common discrete probability distribution functions are the binomial, which we'll be learning about here, the geometric probability distribution function, the hypergeometric, and the Poisson. Now these last 3 we are not going to be covering in this course, unfortunately. The only one you're going to be learning about is the binomial distribution. So let's discuss the binomial distribution. Alright, so here are the characteristics. These things need to be happening in order for us to be in the situation where we have a binomial distribution for a discrete random variable. So there are 3 characteristics of a binomial experiment. Number 1, there are a fixed number of trials or repetitions of an experiment. So the experiment is repeated only so many times, and no more, no less. And that number of trials, the number of times the experiment is repeated, is going to be denoted by lowercase n. Number 2, in each of these n trials, right, in each of these n repetitions of the experiment, there are only 2 possible outcomes. That's why this is given the name binomial. 2 names, 2 outcomes in each trial. There are only 2 possible outcomes for each trial. We can call them a success and a failure, right, depending on what we deem to be a success and what we deem to be a failure, okay, or not success. Now some special notation, some letters you're going to come across. the letter p, lowercase p, will represent the probability of a success on a single trial. All right, so probability of success on the first trial, the second trial, the third trial, and so on, but on a single trial. And the lowercase q, you'll see, will be the probability of a failure on one trial, or not success. Now, if this is the probability of success and this is the probability of not success, right, of failure, then their sum should be equal to 1. Remember complements, the complement rule for probability? The probability of an event plus the probability of not that event should have been, will always be equal to 1, and that's what we're seeing here. All right, and then the third condition, in order for you to be in the binomial distribution scenario, in order for you to be looking at a binomial distribution of a discrete random variable, these n trials that were mentioned, the repetitions of the experiment, the n trials must be independent. Independent, meaning the outcome of one trial has no effect whatsoever on the outcome of the next trial. Right, every trial, all n of the trials are independent and are repeated using identical conditions. So basically every single trial you're starting again, doing the same exact thing again. So an example of this would be like flipping a coin 20 times. Flipping a coin 20 times. There's 20 trials, right? Each coin flip is its own trial, its own repetition. And every trial, each of those 20 coin flips is independent of one another. And the next, the first coin flip is exactly the same kind of situation as the second coin flip, right? And has no effect on the second coin flip. And the second coin flip has no effect on the third, and so on. And if we considered flipping a heads a success, then the value p would be a half. In this case, flipping a coin, and if I said flipping a heads was a success, then the value of p, the probability of success on each coin flip, would be a half. And the probability of failure, not flipping a head, would also be a half, right? Flipping tails. All right. And because they are independent, these trials, the outcome of one trial does not help in predicting the outcome of another trial. That's basically what I've been saying. Another way of saying this is that for each individual trial, the probability p of a success and the probability q of a failure remain the same. Right, so this p and q value do not change from trial to trial. Each trial is the same as the one before it, and they're independent. All right, so they give an example here. For example, the probability that Joe randomly guesses the correct answer on a test is 0.6. Right, so each question is a new trial. And the probability that Joe guesses correctly on each question is 60%. That's like the value of p. So we will say that guessing correctly is a success. So p, right, the probability of a success on each trial, on each question, is 0.6. Since there are only two outcomes for this event, right, you guess correctly or you guess incorrectly, right, binomial. This is a binomial distribution. So then failure is guessing incorrectly, and the value of q would have to be 0.4. Right, so the probability of getting a problem wrong is 40% if the probability of getting a problem right by guessing is 60%. Again, they have a definition, again reading through what is the binomial distribution. And the binomial distribution is sometimes referred to or known as the Bernoulli distribution, named after Jacob Bernoulli, a famous mathematician. But we'll be using the words binomial for the most part. All right, so let's take a look at a question. All right, so here, Jackie is practicing free throws after basketball practice. She makes a free throw shot, with probability 0.7. she takes 20 shots. We say that making a shot is a success. Okay, so this experiment is, shooting free throws. And, one free throw, the next free throw, the next, every time she shoots another free throw, it's another repetition of the experiment, another trial. So the 20 here, the 20 shots, the 20 free throws, is the number of trials. That would be n. And you notice how in every single one of the choices they have n equals 20. Alright, so you're not getting that part wrong. And if we're considering a success, making a shot, then they tell us here the probability that she makes a free throw each time is 70%. Every time she shoots, the first time, then the second time, then the third time, every single individual trial, every single free throw, according to this, she has a probability of making the free throw of 70%. So this 0.7 would be the P. So it's either this one or this one or this one. All these have P equals 0.7. All right, but then they also want the Q, right? Q is that probability of a failure on each trial. So if success is making the shot, then failure is not making the shot. And remember, P plus Q needs to be 1. So if P is 0.7, Q must be 0.3. Right, so we're looking at this option here. Okay. Hopefully that all made sense with me just talking it out. So now some more parameters of the binomial distribution. All right. Some more numbers, describing the population, right? The random variable itself, all possible outcomes of the random variable x, if you call it x. So the outcomes of a binomial experiment fit a binomial probability distribution. So here's the notation for a binomial distribution for a random variable x. All right, so you've seen random variables before, right? A random variable x has a binomial distribution, then they'll write this x and then this little tilde sign, little wavy line there, and then a capital B for binomial, and then in parentheses the values associated with B. Now the first value here is the number of trials, right? The n trials. So back up in this example, it would have been 20, right? Then a comma, and then right after that the P, that probability of success on each trial. So back up in this example, it would have been the 0.7. So if you see this notation, it means that we have a random variable that fits the binomial distribution, right? We have so many trials, and in each trial there are two possibilities, success or failure, with P being the probability of success on each trial, Q being the probability of failure on each trial. So this is read as, x is a random variable with a binomial distribution. The parameters inside the parentheses are n and p, which I told you about already. All right. Okay. Now, some more things about binomial distributions. Okay. So the parameters of a binomial distribution. So the random variable, if a random variable is binomial, then the values of the random variable that the random variable can take on are the number of successes, right? Usually it'll represent the number of successes, and I'll get into an example, of course, where I make a chart and stuff, right? I'll make a table for you. But x will typically represent the number of successes in the n trials. P represents the probability of success on each trial. Q, the probability of a failure on each trial, as you've already seen. N, the number of independent trials, the number of times you're repeating the experiment. All right. Now, if you recall from section 4.2, remember there were these really crazy formulas for the mean and the standard deviation of a discrete random variable. Remember, for the mean, right, mu, the mean value, the expected value, you took every single possible outcome and multiplied by the corresponding probabilities and then added those products up. Right? Well, when your random variable is a binomial random variable, has a binomial distribution, that simplifies to just the number of trials times the probability of success on each trial. The mean value will be n times p. Simple as that. All right, and then the standard deviation. Now again, remember there was this crazy formula that I took you through in section 4.2, where to find the standard deviation of a distribution of a random variable, you took every value, subtracted the mean, right, found the deviations, then squared those deviations, then multiplied by the corresponding probabilities, and then you added those up, and then took the square root of everything, right? Now, that's for a general discrete random variable. For a binomial discrete random variable, for a binomial distribution, the standard deviation is very simple. It simplifies to the square root of n times p times q. The square root of the number of trials times the probability of success on one trial times the probability of failure on one trial. And again, if you squared this, you'd get what's called the variance, right? Yeah, sigma squared, just npq. All right, so let's get into an example here. Now, again, I mentioned the word Bernoulli before, the name Bernoulli. Remember, for a binomial experiment, any experiment that has just two possible outcomes, success and failure for each trial, and where the n trials are independent and repeated using identical conditions, if you just have one single trial, that a single trial is called a Bernoulli trial sometimes. Okay. All right. So, yeah, they just mentioned that just in passing because some books will have, the word Bernoulli showing up. All right. So they give you an example here. I'm just going to get to a question. All right. So again, some key terms. Let's get to a question where we're given a binomial random variable and asked to calculate, its mean and standard deviation. But now we have these simpler formulas because it's a binomial, right? These formulas, this n times p, right, back up here, this n times p and the square root of npq, these are only applicable to binomial distributions, okay? You can't use these for anything else. All right, so my question. See, according to a Gallup poll, 60% of American adults prefer saving over spending. So, they say let x, capital X here, be this random variable that represents the number of American adults out of a random sample of 50 who prefer saving to spending. And they're asking, what is the mean value mu and the standard deviation sigma of this random variable x? All right. Now, I'm going to show you how we would go about making a chart for this. Now, I'm not going to, this is saying, you have a sample of 50 people, all right, 50 American adults, and you're going person to person and asking them, do they prefer saving over spending? All right. So let me show you what a table for this would start looking like. I'm not going to complete the table, all right, but if I were to make one, what would it look like? All right, so I pulled up hopefully you see the paper on my screen in the lower right corner. So remember how these are made. You have a column where you have possible values of x, right? then another column with the probability that the random variable takes on that value. All right. Now, it was mentioned that, back up here, you look at my cursor, capital X represents, the number of American adults out of a random sample of 50 who prefer saving over spending. All right, so the N here, the number of trials, is 50. Right? The number of trials is 50. And the probability of success on one trial, right, the lowercase p, now this is just one person, not all 50. The probability of success, now success here is, saying that they prefer saving to spending. And according to this poll, 60% of American adults prefer saving to spending. So if you were to ask one of these people at random, do you prefer saving or spending, the probability that they would say that is 60%. So 0.6, right, or 60% for P. That's the probability of, one person preferring saving over spending, the probability of success on one trial. All right, then the value of that Q, right, the probability of failure, the probability that, I pick one person, I go to one trial, and they don't prefer saving over spending. That would be the other 40%, right? If the probability of success on one trial is 60%, the probability of failure on one trial is 40%. And what they would say here is they'd say that X, here, because again, every single trial is independent, and every single trial has only two possibilities, right? Binomial, by, two. Success, they prefer saving over spending. Failure, they don't. So X here is a binomial random variable where you have, 50 trials, comma, and then the probability of success on each trial is 0.6. All right, so you're going to see this notation right here to say that X is a binomial random variable. Right. Now, if I were making a chart, a table for this, X here is representing the number of successes. Right, these number of adults out of a sample of 50 who prefer saving to spending. So what are the possible outcomes? If I take 50 random American adults, there's a chance that 0 of them could prefer saving over spending. That's one possible outcome. But there's also a chance that, only one of them, 1 out of the 50, is a success, prefers saving over spending. There's also a chance that 2 out of the 50, exactly 2 out of the 50, prefers saving over spending. 3 out of the 50, 4 out of them maybe. You see why I'm not going to actually complete this table, because this would continue on. And there's also a chance that all 50 of them, if I pick, again, a random group of 50 people, 50 American adults, there is a chance that all 50 of them could say that they prefer saving over spending. So the possible values of this random variable are 0 successes up to all 50 trials being a success. And then we'll talk about how to calculate these probabilities in another objective. Right? It's still going to come up in this section, but we would try to figure out, all right, what's the probability of picking 50 people, 50 American adults, what's the probability that none of them prefer saving over spending? And I'd write that here. And then, what's the probability that exactly one of them prefers saving over spending? And so on, right? So again, I'm not filling this in. All right. But we're asked for just what would be the expected value, the mean of X, and the standard deviation. All right, I guess I should pull the paper back up. So yeah, now if I knew all these, right, remember one way to find the mean for a discrete random variable was to take every single possible outcome, multiply by their probabilities, and then add them up, right? But in a binomial here, right, since I know that X is a binomial random variable, the mean value of x, right, this mu sub x or mu, again, since it's binomial, this is the only time you can use this formula, it's n times p. The expected value will be 50, and then 60% of that times 0.6, which is 30. Right? Now remember what the mean was, right? It was a long-term average, meaning if I took 50 people over and over and over again and figured out how many of them prefer saving to spending, I would, the more and more I did it, the average would get closer and closer to 30. Right, so if I did it the first time, I took 50 people, say 25 of them preferred saving to spending, so I got 25. Then I took another 50 people at random, and 38 of them, preferred saving over spending. So now I have 25 and 38. Add those up, divide by 2, you get an average. Say I did that 100 times, took 100 different random groups of 50, counted how many people preferred saving over spending in each, and then added them up, divided by 100, to get the average. Remember, the average over time should approach this expected value, this 30. Right, and then this was a measure of center, and then the standard deviation, right, a measure of spread. This sigma or sigma x here. Again, this is only because this is a binomial random variable. We can use this. This is just end up simplifying to, instead of doing all that x minus mu and then squared and then multiplying by the probabilities and adding them up and taking the square root, instead of doing all that, for a binomial random variable, it's the square root of n times p times q. Right? So this is the square root of 50 times 0.6 times 0.4. Alright, so this ends up being 2.8. No, not 2.8. 12, the square root of 12. Because we know that 50 times 0.6 is 30, and then 30 times 0.4, would be 12. Alright, so this is the square root of 12, probably around 5.1 something. Let me see. Pull the calculator up. The square root of 12. 5. This will be 3 point something. 3.46. Alright, so my standard deviation approximately 3.46. Alright, so we have the mean of 30, standard deviation of this variable 3.46. So that's looking like this option here. Right. Again, very, very quick and easy to find the mean and standard deviation of a binomial only for those formulas, random variable. Okay. All right. So next, see, now we're going to compute those probabilities I mentioned. Remember that when I pull this page up again, remember this part here when I was filling in this chart? And I was like, hey, I don't know how to find these probabilities. That's what this objective is about. Figuring out the probability of getting so many successes in your n independent trials. All right, so again, first time I'm seeing this objective, I click on more instruction. All right, so see, determining probability from a binomial distribution at a single success value. Later we'll add more than just a single number of successes. You'll see what that means in a minute. So, to determine the probability of a certain number of successes in a binomial distribution, you must know the number of trials and the probability of just one success, right? That P, right? The probability of getting a success on a single trial. The notation of this probability is, B, like for binomial, and then you have the number of successes you'd like to find the probability of. See, X is the number of successes in the whole experiment. and then a semicolon, and then the number of trials, comma, the probability of success on one trial, p, in each trial. Right, where b denotes the distribution as binomial, right? And then again, I told you what the letters meant. So for example, let's say you flip an unfair coin that lands on tails 80% of the time. What is the probability of getting exactly 6 tails in 10 flips? Right, so the 10 flips are the 10 independent trials, right? Because again, the outcome of one flip has no effect on the outcome of the next flip. So they are independent. So n equals 10. This x, this lowercase x, right? This is the number of successes we're trying to find the probability of, right? So they want to know the probability of getting exactly 6 successes, 6 tails. And the probability of getting a tail on one trial, just one flip, is 0.8. Right? Again, this is an unfair coin, so it's not 0.5. Right? It's weighted toward tails. And they'd write this probability out as b of, and then 6 semicolon. Right? I want to find the probability of getting exactly 6 successes, and there are 10 trials. Probability of success on each trial is 0.8. Now, here's the formula for this. Now I'm going to show you a couple different ways to find these probabilities. Right. So I'm going to pull up a piece of paper now, and I'll show you again a couple ways. One on the with your hands, with just writing it out. Also on a calculator. Right. So the probability the probability of getting, this is exactly, getting, I'll capitalize this word, exactly x successes in n independent trials of a binomial experiment. So lots of words there. Again, this is denoted in your text here in the KnewtonAlta this way. B, and then in parentheses, the number of successes I'd like to find the probability of getting, semicolon, then the number of trials, comma, and then the probability of success on each trial. Now, this is calculated in this fashion. So if you remember back from chapter 3, remember counting? We had counting principles, and we had counting with permutations and combinations. It starts off with a combination. N choose X. So see, this is I have N trials, right? I have N independent trials, and I'm choosing X of those to be a success, exactly X of them. So this is us counting the number of ways to get those X successes in the N trials. That's what this N choose X is for. And then this is multiplied by the probability of getting X successes in one trial. Or not one trial, the probability of getting X successes in these N trials. So remember, the probability of getting a success in a single trial is P, but there are X of them, right? There are X successes. So it's success on one trial and another trial and another trial and X trials, X times. Remember, when you have an AND probability, that will involve multiplication. And these are independent, so just simple multiplication. So I'd have P times P times P times P, X times for the X successes. So this is probability of a success, but to the Xth power. All right, so this part of the formula is giving me the probability of getting those X successes. Getting X successes probability. Sorry about the tiny writing. But then, not only do we have success and success and success and success X times, but then the rest of the, because that's not all the trials. If X of them are successes, the other N minus X trials are failures. So I have failure 1 and failure 2 and failure 3 and all the way up to failure N minus X. Right? The rest of the trials are failures. So not only do I have P to the X, then I have Q to the N minus X, right? This is representing the N minus X failures and the probability of getting that many failures. So this is getting N minus X failures probability in these independent trials. Now, I have the formula written, this way. You just have to remember that Q, remember Q is the same thing as 1 minus P, right? P plus Q should be equal to 1. So that's why they have N choose X. Right? How many ways can I get X successes out of N trials? Times P to the X times, and then they have, 1 minus P in parentheses to the N minus X. But remember, 1 minus P is that Q, right? 1 minus P would be the probability of failure. Okay. And they also refresh our memory as to what N choose X was in the factorial notation. Again, this is from chapter 3. I'm expecting you to know this already. So for example, they give one here. I'll just go to a question. All right, you can read that example on your own. All right, so here. So Jamie is practicing free throws before her next basketball game. The probability that she makes each shot, right? So this is each individual shot, each individual trial. The probability that she makes a shot is 60%, 0.6. So if she takes 10 shots, so that's 10 trials, what is the probability that she makes exactly 7 of them? And it says round your answer to 3 decimal places. All right, so back on some paper here. All right, and I'll also show you how to do this on your calculators. So we have this girl, she's taking 10 shots, right? So N, right, the number of independent trials, right? And her outcome on one shot doesn't affect the outcome on the next shot. So N equals 10. It was mentioned that the probability of making a single shot, right, the probability of success on one shot was 60%, meaning that Q, right, that probability of failure not making a single on one shot was would be 0.4, right? We saw something similar to this earlier. All right. Now, what I'm going to do here, we have a random variable called x, capital X, and x is going to be the number of shots made, the number of successes, right? And we could make a little table if we wanted. Here's remember, little x represents numerical values of capital X, right? And then we have in the next column the probability that capital X equals little x. Right? And let's think about the possible outcomes. Right? Again, if there are n shots, n trials, and x represents the number of shots she makes, what are the possible outcomes? Well, she could make none of them. right? 0 successes in the 10 shots. She could make one of them. She could make just 2 of them, or just 3 of them. Right? And I'll go up to say here, she can make 7 of them, which is what we're asked about, and then all the way up to 10. And that's it, right? Those are the only possible outcomes. Right? She can make none of the shots, or all the way up to she could make all 10 of the shots. And then here, this probability that x equals 0. Remember, the way they're writing it here, the way they're writing it in the book would be this b with 0, 0 successes, and then there are 10 trials. Probability of success is 0.6. And then the way I would calculate this would be, I have 10 trials. I choose 0 of them to be successful, right? Whatever that number is, 10 choose 0, times 0.6, p, right, here it is here, p to the 0 power, right? There are 0 successes, times, and if there are 0 successes, that means that there are 10 failures. Alright, so whatever 0.4 to the 10th is, because this is 1, 10 choose 0 is 1. This is also 1. Remember, any non-zero number to the 0 power is 1. So really I'm just left with 0.4 to the 10th. Whatever 0.4 to the 10th is, that is the probability of missing all the shots. And I would do the same for every single one of these. But what we're asked for is this. For this particular question, we're asked for what's the probability that the number of shots she makes out of these 10 free throws is 7. Now again, the fancy way they're writing it is this capital B, right, telling you we're in a binomial situation, right? Successes and failures. We're trying to find the probability of getting exactly 7 successes, where the number of trials is 10, and the probability of success on each trial is 0.6. So again, same formula, right? Formula is not changing. So this is, I have to find the probability of getting exactly 7 of these shots. There are 10 trials, 10 shots. We choose to make 7 of them. So I have a 10 choose 7 times. Then the probability of success on each trial, at p, that was 0.6, raised to how many successes are there, and that's the 7th power, right? 0.6 to the 7th times, and then if there are 7 successes in the 10 trials, that means there are 3 failures. So I multiply by the probability of a failure on a trial raised to how many were failures, right? 10 minus 7, or 3. All right, I'm going to just punch this in my calculator. Right? And I'll show you also a faster way to do it after I do it this way. All right, so remember where that 10 choose 7, how to enter that. I enter 10, the number 10, hit the math button, go over to that probability area, PRB, and there's NCR. Alright, so here's 10 choose 7. Alright, so this is 120 times, right, it's the previous answer, times, and then I've got 0.6, the probability of success on a trial, raised to the 7 trials that are successes, 0.6 to the 7th, times, and then 0.4 was the probability of failure on a trial, raised to how many failures are there? 3. Right. So we got 120 times 0.6 to the 7th times 0.4 to the 3rd, and this is giving me approximately 0. It says round to 3 decimal places, so 214, but 9 is the next one, so 215. Right. So based on if she has a 60% chance of making 1 free throw, 1 shot, and she takes 10 shots, the probability that she gets exactly 7 of them is about 21.5%, 0.215. 0.215. Now, let me show you another way to enter this on your 84 or 83 calculators. Actually, let me go back to the page. All right, so let me clear this out. Now, an alternate way, another feature that the calculator has, right? Or this probability equals. You hit the now there's a button that says VARS. Above that, it says distra, DISTR. I hit second, variables, and then you start scrolling down here in the distributions area. And eventually, you get to these two things. Now there's two of them, so be careful. There's binom for binomial, PDF, right, which is what we've been studying, right, probability density functions. And then there's binom CDF. Now, you might recall cumulative relative frequencies from chapter 1. This is cumulative distribution function or cumulative density function. So we're sticking with PDF for right now. So I hit enter on the A. See this binom PDF. Binom PDF. And then now if you have a newer one, kind of like mine's a little bit newer, this screen pops up where you enter the number of trials. There were 10 of them, right? 10 free throws. Then you have the P, that was that probability of success on one trial, 0.6. Right? And then the X value is, the number of successes. I want to know what's the probability of getting 7 out of these 10 free throws, exactly 7. And then here's how it comes up. You put the number of trials first. If you have an older one, you're going to have to enter it with commas like this. You put the number of trials first, comma. Then you put your probability of success on each trial. That's where the 0.6 is. See, and then another comma. And then you put the number of successes, the X, right, lowercase x. And hopefully, and you're going to see that this comes out to the 0.215 again, or 0.2149999, right? And then 0.8. Same exact number I got earlier. All right. So this binom PDF, again, PDF is for an exact number of successes. All right. Use the PDF for an exact number of successes. And I'll show you what the CDF gives us in a little bit, that binom CDF. All right. Pardon me. All right, so back to the assignment. And they go through the whole calculation here and all that. Okay. So another one. Now they're just asking for the notation. Right. For the problem below, which values would you fill in the blanks of this? Remember, X represents the number of successes, N is the number of trials, P is the probability of success on one trial. So the probability of saving a penalty kick, or a single penalty kick from the opposing team, is 0.617. So this is that P, right? The probability of actually saving. They're going to consider saving a success and not saving the kick a failure. So this is the P for a soccer goalie. If 7 penalty kicks are shot, so this is the N, right? The number of trials, the number of kicks. What is the probability that the goalie will save 5 of them? 5 successes. So 5 for the X, 7 for the N, 0.617 for the P. Looks like that one. That's the notation for finding, expressing the probability of getting 5 successes out of 7 trials, where the probability of success on each trial is 0.617. Okay, simple enough. this part of the section, this part of the instruction, is where that binom CDF on my calculator is going to come into play. I'll show you why. So this is determining probability from a binomial distribution at multiple success values. So now we're not going to see, what's the probability of getting exactly 7 successes. We're going to see stuff like this. What's the probability of getting at least 3 successes? Remember, that means 3 or more. Or at most 10 successes. That means 10 or less. So you're going to be doing a lot of addition here. All right. Or, and I'll show you how to use, again, I'll show you how to use that binom CDF on the calculator. All right, so same notation and all this, same formulas. Right, let's just get into a problem. They have at most, at least. I'll get into a problem. You can read those on your own if you want. All right, so here, 65% of the people in Missouri passed the driver's test on the first attempt. A group of 7 people took the test. Which of the following situations correctly calculate the probability of at least 3 in the group pass their driver's test in the first attempt? All right. So I am going to do this. All right, I'll bring up a piece of paper. We'll write down this scenario, all the pertinent information. Then I'll actually calculate it. All right. So here, the number of trials, right? The n is the number of people who took this test, right? First person took the test. Did they pass it on their first attempt or not? Second person, did they pass it? Third person, did they pass it, right? So it's pass, fail. This is a binomial situation, right? So n equals 7. That p, right? The probability of a success on one trial, right? One person passing on their first attempt was 65%, they said. So 0.65. Right, and then the q is just, again, the probability of not passing on the first attempt, right? A person not passing the driver's test, 0.35, right? That's just 1 minus p. Right, now capital X, right? This binomial random variable is going to be the number of successes. The number of people in this group of 7 who pass the driver's test. I'll just say the number of people who pass and get a success. And then I can make a little chart. Right? Again, I'm not going to fill this in. But I would, but if you wanted to, you could. Right? You could always do this. So little x, remember, this represents numerical values of capital X, this number of people who pass out of the 7 people who took the test. So if I took a random random group of 7 and ran them through this driver's test for the first time, none of them could pass. That's a possibility. And you'll notice that it's always 0 successes up to all n successes. That one of them could have passed, 2 of them could have passed, just 3 of them, exactly 4 of them, exactly 5 of them, exactly 6 of them, or exactly 7 of them. Right? And then you have the probabilities, right? The probability that x equals 0 and the probability that x equals 1 and so on, right? All the way to what's the probability that all 7 of them pass, right? And you could fill in a chart like this if you wanted to. Right? It would take a while, but you could do it. Now, they're asking, what's the probability? Right? They're asking, what's the probability that at least 3 of the 7 pass? Right? The probability that at least 3, again, of a group of 7, is always assumed here, pass. Now remember, 3 means, at least 3 means 3 or more. 3 or more. So a way to write this would be the probability that, x, right, capital X represents again the number of people who pass, is at least 3, means greater than or equal to 3. That means at least 3, x being greater than or equal to 3. Now if you look at my little table over here, being greater than or equal to 3 represents this chunk of the table, right? Getting 3, having 3 of them be successful, or exactly 4 of them, or exactly 5, or exactly 6, or exactly 7. It's or, right? Having 3 or 4, or 5, or exactly 6, or exactly 7. And remember, with or probabilities, you're using that addition rule. You're adding probabilities. And these are all mutually exclusive events. These are all disjoint. These cannot happen at the same time. Right? You can't have exactly 3 people succeed and exactly 4 people succeed at the same time, right? So it's just the sum of these probabilities. So the probability of having at least 3 pass is, the probability that exactly 3 passes plus the probability that exactly 4 of them pass plus the probability that exactly 5 of them pass plus the probability that exactly 6 of them pass, and then finally the probability that exactly 7 of them pass. So going back here, that is represented here. Now, they're saying select all that apply, meaning that more than one of these might actually do it as well. All right. So let's go back to the table. All right. Let's go back to the page. So this here is one valid way of writing that probability. But I got another one for you. Now remember, this is a perfectly valid probability distribution function. I mean, yeah, I don't know what these probabilities are, but you could find them, right? So another way to do this, another way to express the probability of getting at least 3 successes on these 7 tries. Remember that the sum of all probabilities, right, the sum of this probability column is 1. Remember, when you add up all the probabilities in a probability density function, the sum of all the probabilities is 1. Well, what is the sum of all these probabilities? That would be the probability that you get no successes plus the probability that you get 1 success, exactly 1, plus the probability that you get exactly 2, and then plus, now, see the rest of this? The rest of it would be getting exactly 3, exactly 4, exactly 5, exactly 6, exactly 7, which is this up here, which is this right up here. So the rest of this, from 3 to 7, is this probability I wrote up here, the probability that x is greater than or equal to 3. Right? I'm just putting this instead of all these again. So this is the sum of all the probabilities, and as I said, this should be equal to 1. And then we can solve for this, right? Again, this is the probability of getting at least 3 successes, and we're trying to find this. So solving for this, we'd have the probability of getting at least 3 successes, x being greater than or equal to 3, would be equal to 1 minus, and then this whole sum here, I'd just be subtracting all of this, so minus the quantity probability of x being 0, the probability of 0 successes, plus the probability of 1 success, plus the probability of 2 successes. So this is an alternate way of finding the probability of getting at least 3 successes, which again, back on the website, back on the assignment, is this expression down here as well. See, 0 plus 1 plus 2, and then you do 1 minus that. Now let me show you the actual number. Now, I don't know if they actually want us to find it, but let's actually find this probability. Okay. Now I guess another way to write this too. This expression in the brackets, 0 plus 1 plus 2, that's getting 2 or less successes. That's the same thing as 1 minus the probability of x being less than or equal to 2. Right? There's 2 to 0. That's the upper part of this chart. And there is a way to find this less than or equal to probability with the calculator. Right. You can use that binomial CDF for this. Less than or equal to probability. And let me show you. Okay. So pull up the calculator. Now the long way would be using that binomial PDF. Say I want the probability of 0 successes plus 1 plus 2. Right? So I could do this. Right? We go back to that distribution area and hit alpha A. Right? The A was the binomial PDF. A was binomial PDF, or scroll down to it. There were 7 trials. The probability of success on one trial in this case was 0.65. And I want, first I'm going to do the 0 successes. 0 successes. Alright. And then I'm going to add to this the probability of getting exactly 1 success. So plus, and then I go back again to distributions, hit alpha A, binomial PDF comes up, and then 7 trials, 0.65, and then 1 success. And then I'm going to add one more to this, right? This probability that x equals 2. So again, plus distributions, alpha A, 7 trials, 0.65, but now 2 successes. Right? So now I have this probability of exactly 0 successes plus the probability of exactly 1 plus the probability of exactly 2. Let me show you what this is. 0.055607. Okay. Now, the CDF, right? That binomial CDF, when you enter a number of trials and a probability of success on each trial, and then you're going to enter a number of successes, this gives me the probability that x is less than or equal to x. It basically adds up from 0 to 1 to 2 to 3, all the way up to x, whatever x is. It adds up all the probabilities from 0 up. It's cumulative. Right? The C stands for cumulative. And again, hopefully you remember back to chapter 1 when we had cumulative relative frequencies. It starts from the lowest class, right, the lowest number of successes, and adds up the probabilities until the number of successes you entered. Right? So let me show you that binomial CDF now. So I go second, distributions, and this time I'll scroll down and show you it's at letter B. See binomial CDF. Pull that up now again. Please pay attention to the difference at the top here, CDF versus PDF. Now it's the same stuff, 7 trials. The probability of success on each trial was 0.65. That's not changing. This x value I enter now though, this is what do I want to add up to. So if I want from 0 to 2, now it's always starting at 0. Right? This cumulative probability, this CDF always starts at 0 and adds up till the value you enter. So I want the probability of 0 successes plus 1 plus 2. So I'm going from 0 to 2. So I'm going to enter 2 here. And watch this, right? This should be the same as that line I entered earlier where I added each one up individually with that binomial PDF. So I'm going to get 0.055, see, 0.055607, blah, blah, blah. Same number, same exact number. and it's a lot quicker. Right? I don't have to enter 3 different probabilities and add them up. It starts at 0 and adds up until the number I enter, that number of successes. Okay, but it always starts at 0 though, right? The CDF, and adds upward. So this is a very useful tool. And then then 1 minus this, right? 1 minus this previous answer. So this probability, right? The probability of getting 3 or more successes, 3, 4, 5, 6, or 7, to pass this driver's test would be approximately 94%, 0.944. Pretty high. Okay. Yeah, so that's going to be a useful tool for you, the binom CDF, when you're asked about finding the probability of getting at least this many successes, or at most this many successes, or more than, less than, right? Not exactly. Exactly a number of successes is that binom PDF. Right. Okay. And then they actually ask us now, I already told you. Oh, boo. God, they changed it on me. All right. I was about to put 0.944. But look, they changed at least to at most. Haha. So, same kind. Be careful. Be careful. I almost jumped the gun. I almost clicked on this one. Alright, so here, again, same kind of start. Right, 65% of the people in Missouri passed the driver's test on the first attempt. A group of 7 people. Again, n equals 7 here. 7 trials. And p is 0.65. Right, probability of passing on the first attempt, each person passing individually. So what is the probability that at most 3 in the group pass their driver's test in the first attempt? And round your answer to 3 decimal places. All right, so again, I'm going to go back here. Right, so this time, I'm going to do this. Right, we're going to go back to my paper, because it's the same scenario. Right, it's the same scenario as earlier. There are 7 people, 7 trials, 7 people taking this test. The probability of a success on on each trial is 0.65. The probability of failure on each trial is 0.35. X is representing again the number of people who pass. I'd make a chart like this. Just kind of ignore the pink box now. Now we're asked though for the probability that at most, should have capitalized that, at most 3 people pass. So that would be the probability that, capital X here. Now, at most 3 means 3 or less, right? 3 or less. So that's X is less than or equal to 3, which would be the probability that, you get 0 successes plus the probability of getting 1 success, exactly 1, plus the probability of getting exactly 2 successes, and then finally plus the probability of getting exactly 3 successes. Now on my chart here, that would be this part of the box, in the purple, the sum of these probabilities here, right? The sum of the probabilities from 0 to 3. Now, told you earlier, let's switch this over. You could, if I'll pull the calculator up, you can do binom PDF plus binom PDF plus binom PDF plus binom PDF, where n is 7, p is 0.65, and then you got x is 0, x is 1, x is 2, x is 3. You could add all 4 of those up, but that would take a long time. Right? That would take a while. When you're adding up probabilities starting from 0, you go from 0 to some number of successes, use that binom CDF on your calculator. Use binom CDF. If you're adding up probabilities starting from 0, right? You're accumulating them, doing cumulative probability from 0. So on my calculator, let's clear this stuff, right? And so I go back to that distributions area. Alpha B, right? B is the binom CDF. Again, 7 trials. The probability of success on each trial is 0.65 again. But now I'm adding up the probabilities from 0, and again, always starting from 0 with this CDF, up to 3 this time. Binom CDF, with up to 3. So the probability, if I were to take 7 people at random and have them take this driver's test for the first time, and if the probability of at most 3 of them, right, so 0, 1, 2, or 3, passing on the first try is 0.1998 or 0.200, right, if you rounded to 3 decimal places, 0.200, which is this option here. So be careful when reading. Now at most, you can use binom CDF straight away, and you saw earlier with at least, you're going to have to do 1 minus some value to get down to 0, and then use binom CDF. Right, now here they actually add it all up. Right, they take, see, they write it out the long way, 0 to 3 successes. Yeah, much easier to do binom CDF, saving you some time. All right. Now here, this is going to involve, again, just recognizing stuff about the binomial distribution. And this one, they're actually going to have some pictures drawn for you, where you get to take a look at the actual distribution on a graph, almost like a histogram. Right. So here, again, find and visualize probabilities using the binomial distribution. I will click on more instruction. It's the first time I'm seeing this objective. So again, we know that a binomial distribution depends on 2 things, right? The number of trials and the probability of a success in one trial. As the value of n increases, the width of the distribution will also increase, because the possible number of successes will be between 0 and n, right, inclusive. So we're going to actually look at some graphs here, right? See, it's almost like I said, this could be a histogram, these could be rectangles instead of little sticks. But we're going to see pictures of the distribution, okay? We'll play around with this. Also, the center or the mean of the distribution, remember the mean of a binomial was that n times p. So increasing n or increasing p will result in the center of the distribution, right? Remember, the mean is a measure of center, shifting to the right. And if I decrease n or decrease p, it'll shift left. And in order to find the probability of x number of successes using the graph, one simply needs to find the appropriate number. All right, so let's take a look at that situation we had just a second ago. All right, so I'm going to go down. Remember, there were 7 trials, so I'm going to move n down to 7. And zoom this out a bit, move it up. So you see there's only 7 bars, right? 1, 2, 3, 4, 5, 6, 7. Yeah, well, there's 8 actually, because from 0 to 7 would be 8 values. So there are 8 bars. And the probability of success was 0.65, right? 0.65. And then I move down here, the probability of 0 successes is very tiny. See, 6 times 10 to the negative 4th, that's basically, that's just 0.0006. Remember, 10 to the negative 4th means move the decimal place to the left 4 places. Moving the black dot again, the probability of one success in 7 trials is 0.0083. Probability of two successes is 0.0466. The probability of 3 successes, 0.1442, 4 successes, 5 successes, 6, 7. All right. That was a scenario we just looked at. Now look at, again, they said if you increase the value of n, increase the number of trials, it just makes the graph, the histogram, the graph of this wider. All right. So you see, like, go to 100 trials here. You got 101 dots from 0 to 100 successes. And then you see move the black dot around. The probability of the probability of 61 successes in 100 trials. If the probability of success on each trial is 0.65, is a little over 5%, or a little under 6%. And then you see it, remember that the mean is NP. Now if P is 50%, you see how very symmetrical the graph looks? See the distribution is perfectly symmetrical when P is 50%. When P is above 50%, it's skewed left. Right? Remember, see how the mean, the middle, the peak here moves to the right when I increase the probability of success on each trial. The mean gets larger, and remember that when the bulk of it was to the right, and you see how it has this long left tail here, it's skewed left. And then when P is less than a half, when the probability of success on each trial is less than a half, it's skewed right. Right? The long right tail and the bulk of it's on the left. So I'll leave it to you to play around with this, moving the number of trials around, moving the probability of success on each trial around. You can move this black dot here around to see what individual probabilities were. And if you want to compare them to your calculator, you can. Right? Use that Binomial PDF and compare these values to the calculator values, make sure that they're actually the same. But I'll leave it to you to play around with this graph. All right. All right, so then here, I think we're given this is another kind of interactive deal. So a recent study showed that 15% of deaths worldwide are due to heart disease. If 35 deaths were chosen at random, what is the probability that exactly 6 of them were due to heart disease? Right. So the death due, heart disease here is a success. As weird as that sounds. So I have 35 trials, right? They said they took 35 deaths. So I move the number of trials to 35. The probability of a death, an individual death, one trial being due to heart disease was 15%. So the probability of a, quote unquote, success here is 0.15. So I move this probability of success slider to 0.15. Come on. Again, sensitive stuff. So 35 trials, 0.15 probability of success on each trial. They want, what's the probability that exactly 6 of them are due to heart disease? So I move this black dot down here to where we look at the probability of exactly 6 of them. Probability of six successes is 0.1659. So 0.1659. And I just enter the number that they gave me there in the graph. And it's as simple as that, right? Again, I'm just moving some dots around. I know some of these can be a little sensitive. But yeah. All right, so this is a little different. This is just what's n, x, and p. I'll leave that to you. This is easy. What number up here represents the number of trials? What number up here represents the number of successes they want the probability of? And what number up here represents the probability of a success on a single trial, the lowercase p. So I'll cheat on this and leave that to you. It should be a pretty easy one. And I think I can cheat on the rest of them because I've shown you pretty much every kind of problem you're going to get. So this one's similar. Okay. This one's similar to the other one I graphed. Yeah, probably again, you have to move the number of trials, move the probability of success on a trial, move the black dot to the number of successes they're asking you about, and then enter the probability they give you. All right. So I've already done something similar to that. You can do that again. And let's see. Okay. All right. Again, I'll leave this to you. Interpret what it means to have a probability of 8%. Remember, probability usually refers to chance and all that, and that shouldn't be a problem. And this is parameters. Remember, finding the mean and standard deviation. That was n times p for the mean of a binomial variable, and the square root of n times p times q for the standard deviation. And if they want the variance, right, you just take npq, just square that. So I'm not gonna. Yeah, probability again. So I've shown you this. I've shown you problems similar to this, finding the probability of getting so many successes out of so many trials. Yeah, so I'm pretty sure I'm done here. Yeah, I've gone over everything that needs to be gone over. It's a pretty long video, hour 20 some minutes, but still just covered everything. Just wanted to get all the objectives out there, the different kinds of problems you're going to see, and how to work at them. Alright, so hopefully this video is a good guide for you when you work on section 4.3's assignment on your own. Of course, if you have any questions, let me know, and thank you very much for watching.